Imagine you're listening to the universe, not with your eyes, with an antenna. Hours of static, hours of nothing. Then, one clean line appears, a signal that looks intentional. And before anyone can truly react, it's gone. It never returns. Not once. That is the core of today's case file. A signal that showed up, raised every eyebrow in the room, and then disappeared forever. Now, right away, I want to set a rule for this series. We don't make things up. We don't build a story just because the story is exciting. We separate what was observed from what we wish it meant. So tonight, we're doing this like a real investigation, step by step. What was detected? How detections like this actually work? And why it never came back is both important and not automatically proof of anything. Let's start with the basics. When people hear signal from space, they imagine a message, words, patterns, a greeting. But radio astronomy doesn't start there. It starts with something much simpler, energy. A tiny change in the radio spectrum at a specific frequency over a short period of time. Think of it like scanning a vast ocean with a microphone. Most of what you hear is noise. Natural noise, instrument noise, interference from Earth, and random fluctuations. But sometimes you hear a tone. Not music, not speech. Just a tone, clean enough to stand out. And when that happens, the first question is not who sent it. The first question is it real? Because in radio work, the universe is not the only thing you're listening to. You're listening to everything. Satellites, aircraft, ground transmitters, reflections, electronics. Even a tiny glitch in the processing chain can create something that looks meaningful for a moment. So the way we talk about a signal needs to be precise. It's not a story, it's a measurement. Here's a useful mental picture. Imagine you're looking at a heat map. Across the bottom is frequency, from low to high. Down the side is time, from earlier to later. And the color tells you how much power the telescope detected. Most of that picture is messy. A faint background, random speckles, soft stripes. But if a narrow feature appears, it shows up as a bright, thin line, like someone drew a pencil mark across the noise. That pencil mark is what makes these cases famous, because a clean, narrow line feels different. It feels deliberate. But we need to be careful here. Narrow does not automatically mean artificial, and broad does not automatically mean natural. Reality is messier than the headlines. So why does narrowness matter at all? Because many natural radio sources are broad. They spread energy across a range of frequencies. Meanwhile, human technology, our transmitters, often produce narrow signals. A carrier tone, a channel, a steady line. But that's only a tendency, not a law. A thin line can appear because of processing, reflections, or interference. And the natural source can appear narrow depending on how it's detected and filtered. So we don't jump to conclusions. We use narrowness as a reason to investigate harder, not a reason to declare victory. Let me make that practical. If you see a narrow line, you ask, does it stay put? Does it drift? Does it have structure? Does it show harmonics, like multiples of a base frequency? Does it light up in a way that matches known transmitters? Or does it behave like a sky source, moving through the telescope's beam? And even before those questions, you ask something simpler. How was it found? Because detection is not magic, it's a pipeline. A radio telescope doesn't hear like we do. It measures power across frequencies over time. And modern systems search through huge volumes of data with algorithms. They look for anomalies. They flag events that exceed a threshold. They rank them. They record them. Sometimes a human operator notices something strange in real time. Other times, the event is found later in analysis. And here's something people don't realize. These systems catch lots of weird things. Most of them are junk. Interference, local hardware artifacts, known satellite bands, human-made signals bouncing into the telescope from unexpected angles. So the phrase, "we detected a signal," is not rare. What's rare is this: a signal that survives the early filters. A signal that doesn't immediately match an obvious Earth source. A signal that looks clean, isolated, and well-behaved, and then disappears before it can be properly chased. That disappears part is the heart of this episode, because it creates a special kind of uncertainty. You have data, but not enough. You have a clue, but not a trail. Now, why does "it vanished" happen so often in the real world? Because the sky is not waiting for you. The Earth rotates. The telescope is pointed at a moving patch of sky. The system is scanning, switching targets, changing settings, tracking schedules. And sometimes an event is short, seconds, maybe minutes. If it's not still there when you look again, it can be gone forever. It's like catching a single frame of something in the dark. You can replay the frame, you can zoom into it, you can argue about it, but you can't go back in time and ask the universe to do it again. And this is where the phrase "never came back" becomes dangerous, because people treat it like a conclusion. But it's not a conclusion, it's a constraint. It tells you what you cannot do next. You cannot confirm it by repetition, at least not yet. You cannot easily measure a pattern. You cannot triangulate with multiple instruments unless it happens again. So, what are the realistic categories of explanations for a one-off signal? We are not deciding yet. We are mapping the possibilities. Category 1. The event was real and it was cosmic, but it was rare. A single burst, a transient phenomenon, something that happened once or happens so rarely that we just haven't caught the next one. Category 2. The event was real and it was cosmic, but it was geometric, like a lighthouse beam. If the source is directional, you might only be in the beam briefly, and then the beam rotates away or the alignment changes. Category 3. The event was real, but it was local. Not fake, not hoax, just interference, RFI, or a reflection, or a satellite in the wrong place at the wrong time, or a hardware artifact that mimics a clean tone. Category 4. The event is simply underdetermined. We have a fragment of data and multiple explanations fit, so the honest answer is we don't know. Now, quick preview of what comes next, because the next step is the real gatekeeper. In the next part, we ask a simple question: how do you prove a signal is not from Earth? Because if you don't win the fight against Earth noise, you're not listening to space. You're listening to yourself. That's the case. Now we do the work. Imagine you have a perfect looking signal in your data, a thin line, clean, isolated, and then it vanishes. Before anyone talks about space, you have to win one battle first. You have to beat Earth. In radio astronomy, the biggest source of false mystery has a name: RFI. Radio frequency interference. It's the noise we create, often without realizing it. And here's the uncomfortable truth: RFI can fool professionals. It can look narrow, it can look stable, it can even look like it came from a particular patch of sky. This is the most important step in the entire case file. We are asking, how do you prove a signal is not from Earth? Not with vibes, with tests, with logic, with elimination. By the end of this part, you'll understand why a single one-off detection is so hard to certify, and why "it never came back" often means we never got enough time to run every test. First, what counts as RFI? People imagine a radio tower blasting a loud channel, but modern interference is sneakier than that. RFI can be obvious, like a wide, noisy band that screams human, or it can be subtle, like a razor-thin tone that lands right in the wrong place. It can come from satellites passing overhead, aircraft transponders, ships and ground stations, cell towers, Wi-Fi, radar, and even electronics inside the observatory itself. Yes, sometimes the telescope can detect its own building, a cable, a clock, a switch in power supply. Anything that oscillates can leak a tone into the system. And there is another twist. Signals can bounce. They can reflect off terrain, buildings, or even the atmosphere under certain conditions. So a transmitter that is far away can suddenly appear briefly, like it's coming from the sky. Now, if interference is everywhere, how do scientists ever trust any detection? They don't trust it at first, they test it. The first test is the simplest. Does the signal behave like the sky? A real sky source moves through the telescope beam in a predictable way. It rises, peaks, and fades as the pointing changes. If the telescope is tracking a target, and the signal stays the same no matter where you point, that's a red flag, because a true cosmic source should depend on pointing. RFI often does not. So investigators do an on-off test. They point at the target area, on, then they point slightly away, off, then back on again. If the signal remains just as strong when you go off target, it's likely local interference. If it drops away off target and returns on target, that's more interesting. Not a proof yet, but a better sign. But even that test has traps, because a telescope doesn't only hear what it points at. It has side lobes, extra sensitivity in directions you didn't intend. Think of the beam like a flashlight. You aim the bright center at one spot, but there are faint rings of light around it. Those rings can pick up strong transmitters from elsewhere. So a transmitter can masquerade as a sky signal if it enters through a side lobe. And if the telescope moves, the side lobe geometry changes. That can make the interference look like it depends on pointing. This is why professionals don't rely on a single test. They stack tests. They look for consistency across multiple signs. If a signal only appears in one pointing direction, in one frequency bin, for one brief time, you immediately ask, could this be a side lobe pickup? Could this be an aircraft or satellite in just the right position? So what else do they test? They test the frequency behavior. Many Earth sources occupy known bands. Some are licensed and mapped, some are messy and spread, some hop around. But a lot of interference has fingerprints. Investigators ask, is this frequency inside a protected, quiet band? Is it near known satellite downlinks? Does it match common telecom ranges? They also look for harmonics. If you see a tone at one frequency, then a second tone at exactly double, or a series of evenly spaced lines, that often points to electronics or human transmitters. And they check bandwidth. A truly narrow signal is suspicious in both directions. It might be something extraordinary, or it might be a local oscillator leak. So they look for tiny shoulders, modulation, or drift that can separate the two. Now let's talk about drift, because this is a big one. If a signal comes from space, the relative motion between Earth and the source can shift its frequency. That shows up as a slow drift over time. Doppler drift can happen for Earth sources too, especially satellites and aircraft, but the pattern can be different. A fixed transmitter on the ground often appears stable. A satellite often produces a drift that changes smoothly as it moves. A distant sky source might show a drift consistent with Earth's rotation and orbit. So analysts measure: does the frequency slide? How fast? In which direction? Does the drift rate stay consistent? A perfectly stationary tone can be a warning sign. Not always, but often, because the sky is not stationary relative to a moving, rotating planet. Still, here's the catch. If the signal is very short, you may not have enough time to measure drift reliably. That's one reason one-off events are so hard to classify. Another powerful test is duplication. Does any other instrument see it? Does another telescope detect the same event? Does a second receiver chain in the same observatory pick it up? If two independent systems see the same signal at the same time, the odds of a local glitch drop, not to zero, but lower. Some observatories use multiple beams, multiple ears, pointed at slightly different spots. A real sky source should appear strongest in the beam pointed closest to it, and weaker in neighboring beams. RFI, on the other hand, can appear in all beams at once, or in a pattern that doesn't match the sky geometry. That's a major clue. But again, one-off events may happen so fast that you only capture a fragment. And if your system wasn't configured to store full raw data, you may only have a summary. That limits what you can prove afterward. So, investigators also look for human timing. Does the signal appear at the same local time each day? Does it correlate with staff activity? Does it line up with known satellite passes? Does it vanish during maintenance windows? Sometimes the most powerful clue is boring. For example, a signal that appears every day at a predictable time is rarely cosmic. Cosmic events don't care about your local schedule. Humans do. They also watch the shape. Is the signal a smooth rise and fall, like a source drifting through a beam, or is it a hard on-off, like a transmitter keying up? And they check polarization when possible. Some interference has a stable polarization signature. Some sky sources behave differently. It's not a magic bullet, but it's another layer. Now here's where the never came back factor becomes brutal. Because to certify a detection, you want repetition. You want to point again. You want longer integration. You want to try a different receiver. You want another telescope to confirm. But a one-off signal doesn't give you that luxury. You have one capture, and the clock is your enemy. So what do you do in the moment? You do triage. You grab metadata. You save the highest resolution you can. You mark the pointing coordinates. You note the instrument configuration. You log the exact time and frequency. Because later, those details are the difference between interesting story and testable claim. And this is why many famous one-off cases remain unresolved. Not because nobody cared, because the data quality, the context, and the ability to reproduce were limited. The universe didn't give a second sample. So let's summarize the verification ladder, what you would want to see in order. 1. The signal is strongest when the telescope points at the target and weaker off target. 2. The signal does not match common known bands or obvious transmitters. 3. The signal shows a drift pattern that is consistent with the sky source, not a local emitter. 4. The signal appears in the expected beam pattern, not equally in all beams. 5. An independent instrument confirms it, or the same instrument confirms it later. If you can climb most of that ladder, the case gets strong. If you can't, the case stays ambiguous. And with one-off events, you often can't climb far enough. One reason RFI is so persuasive is that it can be quiet. It doesn't always shout. Sometimes it whispers, exactly in the form you're trained to pay attention to. Engineers call these persistent tones birdies, They can come from timing electronics, digital clocks, Ethernet hardware, even cooling systems. A clock tick at one frequency can leak into the receiver chain and show up as a perfect narrow line. And because that line is stable, it looks clean. It looks like something you could build a myth around, but it's just your instrument singing to itself. That's why observatories keep RFI logs. They map their own internal tones. They track what appears when certain systems are powered. They try to identify every house signal the building produces. Then there's transient RFI, the kind that only appears once. And this is where the case file gets tricky. A passing aircraft can reflect a ground transmitter towards a telescope for a few seconds. A satellite can flash a downlink at just the wrong moment. A piece of equipment can switch states and emit briefly. Even a nearby vehicle ignition can create a burst that looks like a clean tone. The key word is geometry. If the path is only open for seconds, you get a one-off, and later, when you look again, the geometry is gone. So never came back can be exactly what you'd expect from a rare interference alignment. Not common, just possible. And that possibility must be tested before anything else. Another layer people forget is the atmosphere. Radio waves don't always travel in straight, polite lines. Under certain conditions, the lower atmosphere can guide radio waves over long distances. It's called ducting. A transmitter far beyond the horizon can suddenly be heard as if it's nearby. Then the conditions change and it vanishes. Higher up, the ionosphere can bend, scatter, or distort signals too. That can make interference flicker, drift, or pulse. And if you only caught a short window, it can look like a cosmic burst. So investigators also check weather and propagation conditions. Not because weather creates alien signals, but because weather changes how Earth signals travel. Now let's talk about how interference sneaks in through the hardware. Because sometimes the signal isn't a real transmission at all. It's a product of mixing. Receivers use oscillators to convert frequencies. If two strong signals enter the system, they can create intermodulation products, new tones at sums and differences of the originals. That means a tone can appear at a frequency where no transmitter actually exists. It's generated inside the electronics, and it can be extremely narrow. This is one reason operators worry about saturation. If a strong local source overloads the front end, the whole spectrum can produce ghost lines. So a clean line can be a symptom of overload, not a message. Even the data processing can create illusions. Radio data is chopped into time slices and frequency bins. It's windowed, it's averaged, it's compressed. If the system flags interference automatically, it may remove chunks of data. And sometimes, removing data can leave behind a feature that looks cleaner than it really was. Also, short events are vulnerable to binning. A broadband blip can land mostly inside one bin and masquerade as narrowband. Not because it truly was narrow, but because of how it was measured. This doesn't mean the data is useless. It means you have to ask, are we seeing the sky or are we seeing our measurement choices? So what is the gold standard response when an interesting signal appears? You want to do two things at once: capture more information and test for locality. If possible, you increase time resolution, you increase frequency resolution, you save raw data. Because details that are invisible in a summary can become decisive later. At the same time, you perform quick discrimination tests, an on-off pointing cycle, a check for simultaneous appearance in multiple beams, and a scan of nearby frequencies for related lines. These are the moves that turn a surprise into evidence, because a signal without context is a rumor, even if it's real data. Let's go deeper on the on-off test, because it sounds simple, but it's powerful. If you point on target and the signal appears, then you point off target by a small angle and it disappears, then you point back on and it returns, that pattern is hard for random local interference to fake. But hard is not impossible. A moving satellite can enter your beam during on and miss it during off. A side lobe pickup can change when you move the dish. So the on-off test improves confidence but doesn't prove origin. That's why you want additional tests that look at the signal's fingerprint, not just its presence. One fingerprint is spatial behavior. If you have multiple beams, the signal should peak in one beam and drop in the others in a predictable way. If it appears equally in all beams, that suggests a local source entering the system broadly. If it appears strongest in a side beam, that suggests a side lobe pickup or a nearby emitter. Some facilities also use reference antennas that listen specifically for local RFI. If the reference antenna sees it strongly, while the sky beam sees it too, that's a warning. Again, not magic, just layers of evidence. The theme of this part is stacking weak tests into a strong conclusion. Another fingerprint is time structure. A real transmitter often has human-like switching. It keys on and off sharply. It repeats. It has bursts with consistent spacing. A sky source, when seen through a telescope beam, often has a smoother envelope. It can rise as the beam centers, then fall as it moves away. Not always, but often enough to be useful. Analysts also look for what I'll call edge behavior. Does the signal smear when you change resolution? Does it split into multiple components? Does it vanish when you change polarization? Those behaviors can separate hardware artifacts from real external sources. Now, about satellites, because people underestimate how many there are. A satellite can produce a narrow signal that drifts. It can appear from above, because it literally is above. And it can be present only for a short pass. So investigators will often compare event times to known orbital passes. They check whether a satellite was in view. They consider whether the frequency is consistent with satellite services. The tricky part is that not every transmitter is openly catalogued, and not every signal is easy to attribute. So, we didn't find a satellite match is not the same as there was no satellite. It just means the match was not obvious. This is why the phrase "not an obvious Earth source" is a careful phrase. It doesn't mean not Earth, it means not identified as Earth yet. In practice, investigators assign confidence levels: high confidence RFI, probable RFI, uncertain, interesting, requires follow-up. A one-off signal often lands in the middle, interesting but unverifiable, not because it's fake, because it's incomplete. And that brings us back to our case title. The signal that never came back may have been something real. But without repetition, the best you can do is rank explanations, not prove one. There's also a counterintuitive problem. Removing interference can hide the truth. Automatic RFI excision sometimes deletes the very moment you need. If the system flags a burst as too bright, it may cut it out. Then all you see later is a gap or a softened remnant. So analysts want access to raw or minimally processed data when possible. Because heavy cleaning is great for routine science, but it can erase the forensic detail that a case file depends on. If you're wondering, why not just keep listening to the same spot forever? There are practical limits. Telescopes have schedules. Receivers cover limited bandwidth at a time. Storage is expensive. And many searches trade depth for coverage. They scan wide areas rather than stare at one point. So when an event happens, follow-up can be delayed. And for transient phenomena, delay is deadly. If it was a one-time burst, it's already gone. If it repeats on a long cycle, you might miss the next window. Here's what good evidence looks like in practice. It's not just the signal itself, it's the context. You want the exact timestamps, the pointing coordinates, the receiver settings, the bandwidth and resolution, the calibration state, and any parallel logs from the facility. Because later, when someone asks, could this be interference? Those details let you test. Without them, you can only argue. And one last point before we move on. When you see a sensational headline about a mysterious signal, the most useful question is not, what do you think it is? It's this. What tests did it pass? Did it appear only on target? Did it show a consistent drift? Was it seen in a single beam pattern? Was there an independent confirmation? Was local RFI ruled out with evidence, not assumptions? If the answers are missing, the case is not solved. It's not debunked either, it's simply incomplete. Now we're ready for part 3, the realistic cosmic explanations that can produce a one-off signal, without inventing a story. Now that we've built the filter for Earth noise, we can finally ask the next question. If the signal was real, what could space do that looks like a one-time event? Here's the key idea for part 3. In astronomy, transient is normal. The sky is not a steady background. It flickers, it flares, it pulses. It sometimes does something once and then never again, at least in our lifetime. So a signal that never came back is not automatically extraordinary. It's a category, and that category has real, physical members. But we also have to stay honest. Some cosmic explanations fit certain kinds of signals better than others. A wide burst is different from a razor-thin tone. A drifting line is different from a stable one. So we'll build a realistic map, not a story, a map. In this part, we'll look at 3 big buckets: signals produced by the source itself, signals shaped by geometry, like a lighthouse, and signals modified by the space between us and the source. Let's start with the simplest concept, a source that truly emits radio energy. Not a message, just physics. Some objects in space are natural radio transmitters. They generate strong magnetic fields, plasma, and shock waves. They can produce bursts, pulses, and sometimes narrow features. The most famous radio lighthouses are pulsars. They rotate. Their beams sweep across space. When the beam crosses Earth, we detect a pulse. Now here's the important part. Not all pulsars behave like perfect clocks. Some are intermittent. Some shut off for long periods. Some produce rare bursts. Some can appear for a short window and then go quiet. So the idea of it showed up once can be explained by real classes of objects. But whether it matches our specific signal depends on the shape, bandwidth, and time behavior. If the detection was a short event, one candidate class is burst-like sources. A burst can be strong, brief, and rare. Fast radio bursts, FRBs, are a real example of extreme bursts. Some repeat, some do not, at least not yet. And the one-off FRB can absolutely fit the phrase "never came back." But FRBs have a key fingerprint: dispersion. As the burst travels through plasma, lower frequencies arrive slightly later than higher ones. That creates a characteristic sweep in time-frequency plots. So if a detection shows that kind of frequency-dependent delay, it strongly supports an astrophysical origin. It doesn't tell you who, it tells you not local. However, many famous thin-line detections are not FRB-like. They are narrow, sometimes steady, sometimes short, so we also need natural phenomena that can look like a thin spectral line. And those exist too. This is where a lot of people get surprised. Nature can create narrow band emission, extremely narrow. The strongest example is a cosmic maser. A maser is like a natural laser, but at microwave and radio frequencies. Certain molecules in space can amplify radiation in a very specific transition. That produces a sharp spectral line. So yes, space can produce something that looks like a clean, narrow tone, without any intelligence behind it, just chemistry and physics in the right conditions. Masers are observed in real environments, star-forming regions, around evolved stars, and in some active galaxies. They can be bright, they can be variable. Sometimes they flare, sometimes they fade. That variability is important, because it gives you a natural path to a one-time detection. Not because it happened only once in the universe, but because it crossed your detectability threshold only once. Let's talk about that threshold idea, because it matters. A source can exist continuously, but you only detect it when conditions are right. Maybe the source brightened. Maybe your telescope was pointed at the perfect spot. Maybe background noise was lower. Maybe propagation effects made it spike. Think of it like hearing a faint sound in a crowded room. The sound might be present the whole time, but you only notice it when the room gets quiet for a second. So, never came back can mean it never came back above your detection threshold, not that it stopped existing. This is one reason science loves repeat observations. If it repeats, you can integrate longer. You can build signal to noise. You can climb from maybe to measured. If it doesn't, you're stuck with a snapshot. Now, another cosmic source of narrow features is spectral line emission more generally. Hydrogen, hydroxyl, water, and other molecules produce known lines. Some are protected bands, some are not. So frequency placement can be a big clue if you have precise metadata. So far we have two realistic cosmic buckets, burst-like phenomena and narrow spectral lines like masers. Now let's add a third, geometry. Geometry means the signal depends on alignment, not because the source is choosing you, but because the physics is direction. A rotating object with a beam is the cleanest example. If the beam sweeps past Earth for a short window, you see it. If it doesn't, you don't. This is why lighthouse models appear in real astronomy. A pulsar beam can be narrow. A magnetized object can emit in cones. Even certain plasma processes can favor specific directions. Now add one more layer. The source might not be steady. It can have active and quiet states. So you get a double rarity. You need the beam alignment and you need the source to be on. That combination can produce a one-off detection without invoking anything exotic. It's rare, yes, but rare is not impossible. Another geometry effect is occultation. Sometimes a signal path is blocked. An orbiting body can pass in front. A dense plasma region can absorb or scatter the emission. You might catch the source only during a brief opening. And there's also the idea of gravitational lensing. A massive object can bend paths and temporarily amplify a background source. It's like a cosmic magnifying glass. Most lensing events are subtle in radio, but amplification can, in principle, push a marginal source above threshold briefly. Then it fades back below. That is another, never came back pathway. Now we move to the third major bucket, the space between us and the source. Because sometimes the source is steady, and what changes is the medium. Radio waves travel through plasma. The interstellar medium is not smooth, it's turbulent. It has density variations, and those variations can focus or defocus radio waves. This is called scintillation. It's the radio version of stars twinkling. In visible light, twinkling happens because Earth's atmosphere distorts starlight. In radio, Twinkling can happen because plasma in space distorts radio waves. The signal intensity can fluctuate, sometimes dramatically. So a steady source can appear to flash on and off, not because it's turning on and off, but because the path is focusing energy toward you for a short time. Then the focus shifts and it fades. This is a real mechanism, and it can create the illusion of a transient. You might detect the source once, strongly, and then not detect it again for a long time. There's an even stronger version sometimes discussed: plasma lensing. A dense region can act like a lens and create sharp boosts. If you pass through the lensing geometry briefly, you get one peak. That can look like a one-time event in your data. Now, here's the honest complication. Some of these cosmic explanations fit broadband bursts better than razor-thin tones. Some fit narrow lines better than short spikes. So classification depends on the details you captured. If your event was a clean narrow line with no measurable drift, that leans toward a stable transmitter, a spectral line, or a local oscillator artifact. If it had drift, that opens more possibilities. If it had dispersion, that strongly supports an astrophysical burst. But remember, short duration limits your diagnostics. If the event lasted a few seconds, you might not have enough time to measure drift. You might not have enough bandwidth to see dispersion. You might only have a summary, not raw data. So you have to keep your confidence proportional. This is why one-off events are hard. They sit in the gray zone where multiple models survive. And the best you can do is rank them, not prove them. So how do scientists rank them? They ask, which hypothesis predicts what we actually see, and which hypothesis would also predict a plausible no-repeat outcome. Let's build a practical ranking checklist for cosmic explanations. If the signal is narrow and sits at a known spectral line frequency, natural line emission becomes plausible, especially if the frequency matches known molecular transitions. If the signal is burst-like and shows dispersion across a wide band, a transient astrophysical event becomes plausible, FRB-like, magnetar-like, or other plasma processes. If the signal shows a consistent drift rate over time, that can be consistent with relative motion, but it also can be consistent with satellites. So drift is a clue, not a verdict. If the signal repeats with a stable period, that strongly supports a rotating engine, a pulsar-like beacon. But our case is the opposite. It didn't repeat. So we focus on intermittent engines and threshold effects. Now, what about magnetars? Magnetars are neutron stars with extreme magnetic fields. They can produce flares and radio outbursts. Some can turn on in radio temporarily and then quiet down. That gives a natural one-off pathway again.
But again, magnetar events usually have broadband structure. So, for a narrow tone, maser-like or spectral line explanations often fit better. And here's another subtle point. Even a spectral line can vary. Masers can flare. They can change intensity due to pumping conditions, shocks, or geometry inside the cloud. So you can catch a flare once and miss it later. Also, your telescope may only have observed that exact region briefly. If follow-up time is limited, you can easily miss variability. And variability is the enemy of certainty. So, never came back can be a combination of three ordinary things. The source was variable, the observation window was short, and the detection threshold was harsh. Now let's address a common misunderstanding. People hear a signal that looked intentional and assume it must be engineered. But intentional is a human aesthetic. Nature can produce clean patterns, especially when our instruments filter, average, and display data in simplified forms. So part of doing real case files is resisting that instinct. We don't ask, does it look like a message? We ask, what physical process could generate this measurement? Now, one more realistic cosmic angle. the solar system itself. Planets can produce radio emission. Jupiter is a famous example of strong natural radio output. It's not narrow like a single tone, but it reminds us that space radio can be close. And the Sun is a giant radio source. Solar radio bursts can be intense and complex. Sometimes they create features that look structured in frequency and time. They can also be highly intermittent. But if a telescope is looking away from the Sun, solar contribution can still leak in through side lobes. So a solar event can mimic a sky signal if your instrument picks it up indirectly. That's why cosmic and local can blend, not in meaning, but in detection. So the cosmic category is not a clean box. It includes real astrophysics, and it includes the reality that our instruments are imperfect listeners. At this stage, a professional response is to assign likelihoods, not to claim certainty. For a one-off narrow line, you often end up with probable interference, possible spectral line, uncertain transient, and unknown. The ordering depends on the data. So, what would strengthen the cosmic explanation? What would make it feel less like a ghost and more like a phenomenon? First, repeated detection of the same line at the same sky coordinates. Even if it's rare, repeating even once turns a story into a dataset. Second, a match to known astrophysical line behavior. For example, a line width consistent with thermal and kinematic broadening, a slight Doppler shift consistent with a rotating region, a correlation with known maser environments. Third, multiple beam localization. If the signal peaks in the correct beam pattern, that supports a sky origin. If it appears everywhere equally, it leans local. Fourth, broader context. Is the region known to host star formation? Is there a known object there? Is the signal near a frequency where known molecules emit? These don't prove it, but they guide probability. Now, we're not doing a specific historical case name here. We're building a general evergreen model, because the same logic applies to new detections. And there will be new detections. So let's state the honest conclusion of part 3. A signal that never came back does not force you into one explanation. It opens a menu, and space has real items on that menu. 1. Intrinsic transients, bursts that truly happen once or rarely. 2. Intermittent engines, sources that switch states. 3. Spectral lines, natural narrow emission like masers. 4. Propagation effects, scintillation and plasma lensing that push a steady source above threshold briefly. 5. Geometric chance, beam alignment, occultation, and other one-window effects. And the reason we don't pick one right now is because one-off events often lack the detail needed to decide. That's not a flaw in logic. That's the reality of limited data. So our responsible move is rank plausible cosmic models, keep RFI in the running until it's eliminated, and label the outcome with the right confidence. Now, in the next part, we shift from physics to the human layer. Why do some one-off signals become legends? Why do headlines outrun evidence? And how do you keep your brain from writing fiction in the gaps? Before we leave, one final thought. A lot of people think the most exciting answer is, it was something intelligent. But in real science, the most exciting answer is repeatability. If you can predict when and where something will reappear, you can test it. If you can test it, you can learn. And learning is more powerful than guessing. So when a one-off signal appears, the real question becomes, what follow-up strategy would give us a second chance? Do we stare longer? Do we coordinate multiple telescopes? Do we widen the recorded bandwidth? Do we keep raw data for forensic analysis? That's the difference between a legend and a measurement program. And it's also why modern transient astronomy
is built around rapid alerts and coordinated observing. Because transients are real, and the only way to understand them is to catch them again. Okay, we've mapped the real cosmic pathways. Now we're ready to talk about why the story spreads faster than the data. Part 4 is about discipline, how to enjoy the mystery without breaking the rules, how to talk about uncertainty without sounding boring, and how to spot the difference between this is unresolved and this is unexplained, because those are not the same. Unresolved means we don't have enough evidence yet. Unexplained means no explanation exists. Science almost never gets to say the second one, it lives in the first. So next, we'll build a mental filter, how myths form, how framing changes perception, and what questions bring you back to reality. Let's go to part 4. We've done the physics. We've built the filter for Earth noise. We've mapped the real cosmic pathways. Now comes the part that decides whether a case file becomes science or becomes a legend. Part 4 is about the human layer. Not because humans are the problem, because humans are the amplifier. A one-off signal is like a spark. Data gives you the spark, and attention gives it oxygen. So the question is, why do some one-off detections turn into global stories? Why do they feel bigger than they actually are? And how do we keep ourselves honest without killing the mystery? Tonight, we are going to build a mental checklist, a way to enjoy the case without turning it into fiction. Let's start with a simple truth. Humans don't like unfinished stories. If something repeats, the brain relaxes. You can test it again, you can measure it, you can label it, it becomes a thing. But when something happens once and disappears, the brain does the opposite. It becomes alert. It tries to complete the pattern. It tries to guess the missing pieces. That pattern completion instinct is not stupidity. It's survival software. We are built to detect meaning fast. Because in the real world, missing a pattern can be costly. So a one-off signal hits the brain like this. I saw something. I don't understand it. I need closure. And if reality doesn't provide closure, imagination offers it. This is where language becomes dangerous, because the words we use shape what people believe. Think about the difference between these two phrases: unresolved signal, unexplained signal. Unresolved means we don't have enough evidence yet. Unexplained sounds like no explanation exists. Most real cases are unresolved. Headlines love the word unexplained, because unexplained feels like a doorway. It promises something dramatic. Another example, not identified as Earth. This often turns into not from Earth. Those are not the same. Not identified means the investigation is incomplete. Not from Earth is a conclusion. So in this part, we're going to slow down the language, because careful language is not boring. Careful language is how you keep the case file real. Now let's talk about the myth engine. How does a one-off signal turn into a legend? It usually follows a predictable path. Step 1. Detection. A real measurement, a real anomaly in data. Step 2. Framing. Someone describes it with emotional words. Strange, perfect, intentional, impossible. Step 3. Compression. The story gets simplified for speed. Details disappear. Caveats get removed. Uncertainty gets trimmed away like dead weight. Step 4. Escalation. Each retelling pushes it a little further. Maybe it becomes classified. Maybe it becomes confirmed. Maybe it becomes a message. And step 5. Permanence. The legend outlives the original data, because most people never read the original paper. They read the story of the story.
There is also a reason the internet loves one-off mysteries. They create endless content. A solved case is a full stop. An unresolved case is an open loop. And open loops keep people watching. That's why you'll see the same headline recycled again and again. Mysterious signal detected. Even if nothing new happened. Even if the event is old. Even if the science hasn't changed. Because the emotional product is not knowledge, it's suspense. Now, suspense is not evil, but it becomes a problem when suspense replaces accuracy, when the show becomes more important than the evidence. So the goal is balance. Keep the tension, keep the wonder, but do not lie to your own brain. Here's the first tool for staying honest. Separate observation from interpretation. Observation is what the instrument recorded. Time, frequency, strength, beam pattern, metadata, those are facts. Interpretation is what you think it means. Interference, satellite, maser, burst, unknown, those are models. Most bad stories blend the two. They say, we observed a signal, therefore it was a message. That is a jump. A clean case file says, we observed X. These are the models that can produce X. Here are the tests we ran. Here is what we can and cannot conclude. If you can keep that structure, you can talk about mysteries forever and still stay real. Second tool. Never fall in love with the first explanation you hear. The first explanation is usually designed for impact, not accuracy. It might be an exciting hypothesis, or it might be a dismissive debunk. Both can be wrong when data is limited. So instead of asking, what is it? Ask, what did it pass? Did the event appear only on target? Did it show drift consistent with relative motion? Was it seen in multiple beams in a sky-like pattern? Was it independently confirmed? Were known local tones ruled out? If the answers are unknown, then your conclusion must also be unknown. That is not weak, that is disciplined. Third tool. Watch for emotional words that feel like evidence. Words like perfect, clean, impossible, too narrow, too precise. Those words can be true descriptions, but they are not explanations. Perfect can also be the signature of electronics. Clean can be a local oscillator. Precise can be a clock signal. So whenever you hear an emotional adjective, translate it into a technical question. If someone says, it was too clean to be natural, ask, what natural mechanisms were tested? Were masers considered? Were spectral lines checked? Was the display resolution and binning examined? This translation habit is how you stay grounded. Not cynical, grounded. Now let's talk about authority, because it's another myth accelerator. When someone says scientists confirmed, it sounds final, but science rarely works like that. Science is confidence levels. Science is replication. Science is updates. A serious report often sounds cautious, candidate, possible, consistent with, requires follow-up. And the internet often translates caution into certainty, because certainty spreads faster. There is also the opposite problem. Sometimes a case is dismissed too fast. Just interference, just a glitch. That can be lazy too, if it isn't supported. A real debunk is not a vibe. A real debunk points to a specific mechanism and shows how it matches the data. So, in a healthy case file, you treat both extremes the same way. Show the tests, show the match, or admit uncertainty. Here's a concept that helps: information decay. Every time a story is repeated, technical detail tends to drop. What remains is the emotional skeleton. Time and frequency become a signal. Beam patterns become a telescope heard it. Calibration becomes it was strong. Confidence levels become it was confirmed. And the more the detail decays, the more space there is for imagination to fill. That's why archival thinking matters. If you care about truth, you go back to the earliest version, the first report, the rawest description, the closest source. In this playlist, that's what we do. We treat every case like evidence in court, where the original document matters more than the rumor. Now, how do you talk about uncertainty without losing attention? This is important, especially for long-form audio. The trick is to make uncertainty feel like a process, not a dead end. Instead of saying, "We don't know, end of story," you say, "Here's what we know, here's what we can test, here's what would decide it." That turns uncertainty into a roadmap. It gives the listener something to hold. You can also use simple probability language, not numbers you can justify, just rankings. Most likely, plausible, unlikely, unknown. And you always tie those rankings to reasons, not opinions, reasons. Because reasons are what separates case files from campfire stories. Let's build a quick anti-myth checklist you can use on any viral claim. Question 1. What exactly was observed? Not what it looked like, what was measured. Question 2. What tests were run to exclude Earth sources? On-off pointing, multi-beam behavior, frequency checks, timing checks. Question 3. Is there independent confirmation? A second telescope, a second receiver chain, a second dataset. Question 4. What would we expect to see if the claim were true again? A repeat, a drift pattern, a dispersion signature, a predictable window. Question 5. What information is missing, and is the missing information convenient for the story? If you can't answer most of this, the honest label is incomplete, not solved, not debunked. Incomplete. There's one more psychological trap we should name. It's called the narrative upgrade. A narrative upgrade happens when someone turns uncertainty into intention. A brief anomaly becomes a warning. A single burst becomes a ping. A narrow line becomes a beacon. A failure to repeat becomes they stopped transmitting. Notice what changes. We replace physics with motives. Motives are not measurable. Motives are not data. Motives are story. So, whenever you catch yourself thinking in motives, pull back. Replace motives with mechanics. Replace they with it. Replace message with measurement. You can still be amazed, but you stay anchored to what can be tested. Now let's connect this back to our title, The Signal That Never Came Back. That phrase is emotionally perfect. It sounds like a mystery with personality, like the universe teased us. But the scientific translation is colder. Single event detection with insufficient follow-up. And that translation matters because it pushes you toward the right next step, not speculation, follow-up strategy. So the best mindset for a one-off case is not belief, it's curiosity with discipline. You ask, what would we need to see next time to decide? What should be recorded? What should be checked in real time? Who should be alerted? That mindset turns myths into research, and research is how mysteries get smaller without becoming boring. If you want a simple rule, the more extraordinary the implication, the more boring the evidence must be. Boring evidence means multiple detections, consistent parameters, independent confirmation, and repeatable behavior. If the only evidence is a single dramatic moment, then the correct posture is humility. Because drama is easy to manufacture, by nature, by noise, by coincidence. Humility does not mean dismiss it. Humility means don't claim more than the data can carry. This is especially important online, because audiences reward certainty. But reality rarely gives certainty on day one. So if you build your brand on disciplined uncertainty, you stand out, not by yelling louder, by being reliable. Now we're ready for the transition. Part 5 is where we bring everything together. We won't solve the case with fantasy. We'll do something more useful. We'll build a practical conclusion, a ranked set of explanations, what evidence would shift the ranking, and what a modern follow-up strategy would look like. Because this is the real promise of space case files. Not answers for everything, but a method, a way to think, a way to test. So, if you ever see a viral headline again, mysterious signal detected, you'll have a toolkit. You'll know what questions matter, and you'll know when someone is selling a story instead of evidence. One last reminder before we move on. Mystery is not the enemy. Laziness is. You can be fascinated and still be strict. You can be curious and still be careful. You can chase the edge of the known and still respect the rules. That's the tone of this series. We don't mock the unknown. We don't worship it either. We investigate it. Okay, we've covered how legends form, we've covered how words distort meaning, and we've built a checklist to keep the case file real. Now, let's go to part 5. The conclusion, the ranking, and the one thing that matters most. What would count as real proof next time? Part 5 is where we stop voting in theory and land on actions. What to record, what to test first, what would raise confidence, what would lower it, and what unknown should look like when it's communicated honestly. Because if a signal like this ever appears again, the goal is not to go viral. The goal is to be ready. Let's finish the file. We've reached the end of the file, not the end of the mystery, just the end of what the evidence can responsibly support. Part 5 is the conclusion, but it's not a Hollywood conclusion, it's a case file conclusion. A ranked set of explanations, a list of tests, and a clear definition of what would count as real proof next time. Because with one-off signals, the most honest answer is often, we can't close the case, we can only tighten it. So tonight, we're going to do 3 things. 1. Summarize what the detection means and what it doesn't. 2. Rank the plausible explanations without pretending certainty. 3. Design a follow-up plan that could convert one look into a dataset. First, what does a one-off detection actually mean? It means the instrument measured an anomaly in radio power at a specific time and frequency. That's it. Everything else is interpretation. It does not automatically mean a message, a beacon, a visitor, or intent.
And it also does not automatically mean a hoax, a mistake, or nothing. It means we have a single event with limited context, and that limitation is the key constraint on every conclusion that follows. So the most responsible sentence you can say is interesting but incomplete. And if you can say that without embarrassment, you're already doing better than most headlines. Now let's rank explanations. This is not a verdict, it's a probability ladder based on what typically happens in radio work. Rank 1 by default is always interference until proven otherwise. RFI is common, RFI can be deceptive, and the burden of proof is on not Earth. Rank 2 is orbital sources. Satellites and aircraft can produce narrow signals, drift, and one-time windows, and the number of transmitters in orbit is not small. Rank 3 is instrumental artifacts. Local oscillators, birdies, intermodulation, saturation, processing effects. They can generate clean features that look meaningful. Only after those do we lean into cosmic explanations. Not because cosmic is impossible, because Earth and hardware are the most frequent culprits. So cosmic explanations sit in the next tier. Rank 4 is natural narrow emission, like spectral lines or maser-like behavior. Space can produce clean, narrow features, and those features can vary in time. Rank 5 is transient astrophysical events, bursts, intermittent engines, magnetar-like activity, plasma processes, especially if the event shows dispersion or broadband structure. Rank 6, the most extreme tier, is deliberate engineered transmission, a true beacon, a true message, a true artificial source beyond Earth. Notice where that sits, not at the top, at the bottom of the ladder, because it requires the most assumptions, and science tries to minimize assumptions. This doesn't mean never. It means extraordinary claims require extraordinary evidence, and one-off data is rarely extraordinary evidence. Now, what would move an explanation up the ladder? This is where the case file becomes useful, because we can define triggers. If the event appears equally in multiple beams or appears off-target, interference becomes more likely. If the event appears strongly only on target and weakly off-target, cosmic becomes more plausible. If the event has harmonics or evenly spaced comb lines, electronics become more likely. If the event matches known satellite bands or aligns with orbital passes, orbital becomes more likely. If the event shows dispersion across a wide band, astrophysical becomes much more likely, because dispersion is difficult for local interference to mimic in the same way. So the ranking is not opinion, it's conditional, and the conditions are testable, if you have the data. This brings us to the central question: what counts as real proof? In science, proof is not a single dramatic moment. Proof is repeatability plus independent confirmation. So the gold standard for a case like this would be the signal reappears at the same sky location with similar parameters, and it is detected by independent systems. Even one repeat changes everything, because a repeat allows targeted observation, longer integration, higher resolution capture, and real discrimination tests. Without repetition, you're mostly doing forensics. With repetition, you can do experiments, and experiments are how mysteries become knowledge. So what exactly would we want to record next time? Let's be specific. 1. Raw or minimally processed wattage data, if possible, because raw data preserves fine structure that summaries can erase. 2. High time resolution, because drift, pulses, and modulation live in time. 3. High frequency resolution,
because narrow lines, substructure, and harmonics live in frequency. 4. Full metadata, pointing coordinates, exact timestamps, receiver chain settings, calibration state, beam configuration. These details are not boring, they are what make the case testable. 5. Parallel RFI monitoring, reference antennas, local spectrum monitors, logs of site activity, because eliminating Earth sources requires evidence, not confidence. If you capture those 5 layers, you turn a ghost into a specimen. Now let's design a follow-up plan. Imagine the signal appears again tomorrow. What do we do in the first minute? First, log recording at maximum resolution you can afford. Do not rely on summaries. Save everything you can. Second, run an immediate on-off test if the signal persists long enough. On target, off target, back on. Record each pointing. Third, check multibeam behavior. Does the signal peak where the sky position predicts, or does it appear everywhere? Fourth, widen the observed bandwidth around the event. If you only record a narrow slice, you miss dispersion and related features. A wider band gives you fingerprints. Fifth, trigger coordination. Send an alert to other instruments. If another telescope sees it, the credibility jumps. If they don't, that also provides information. Now, what if it doesn't persist? What if it's a 2-second event again? Then you switch strategy. You treat it like a transient program. You create an alert pipeline. You save buffers. You keep rolling storage that can capture moments before and after a trigger. Many modern searches do exactly this. They maintain a short ring buffer of raw data. When an event triggers, the buffer is dumped to disk. That way you don't only save the moment you noticed, you save the lead up too. If you're trying to catch something that rarely repeats, this buffer strategy is the difference between I saw a line and I have structure, drift, and context. So the real upgrade in a case like this is not a new theory. It's better capture, better timing, better coordination. Now let's talk about what not to do, because bad follow-up can freeze a myth in place. Don't jump to "it was a message." That locks your thinking into motives instead of mechanisms. Don't jump to "it was nothing." That locks your thinking into dismissal instead of testing. Don't hide uncertainty. Uncertainty is not weakness. Uncertainty is a description of the evidence. And don't rely on a single screenshot of a plot. Plots are interpretations of data. The data matters. The settings matter. The pipeline matters. If you want your audience to trust you, teach them this rule. The more extraordinary the implication, the more documentation you need. That's not cynicism. That's quality control. Now, can we say anything emotional without breaking the rules? Yes, because the emotional truth of this case is real. A one-off signal is haunting, not because it proves anything, but because it reminds you how small your sample is. We listen to a vast universe through a narrow straw. We catch minutes of data from regions that have existed for millions of years, and we expect clarity. So when a signal appears once and vanishes, it exposes the gap between the universe and our tools. That gap is where legends are born, but it's also where science grows. Because every time we fail to capture enough, we improve the capture, we refine the filters, we build faster alerts, we coordinate better. So the correct emotional response is not belief, it's motivation. Be ready next time, because next time is how unknown becomes understood. Let's give the case file its final label. Based on what we've built, the honest label is single event candidate of uncertain origin. That may sound plain, but plain is powerful, because it protects you from lying. You can still say, it was real data, it was interesting, it passed some initial filters, and it failed the one test we wanted most, repeatability. And because it failed repeatability, the case remains open, not in a supernatural way, in a procedural way. Now, what would close the case? Two paths. Path 1, a repeat with enough context to classify it. Then it becomes interference, orbital, instrumental, or astrophysical. Path 2, a clear identification of the original event via logs, a matched satellite path, a known internal tone, a propagation event, something that maps cleanly to the timestamp and frequency. Until one of those paths happens, the file stays open. And that is okay. Now let's turn this into a takeaway for the audience. If you remember only one thing from this series, remember this. Mystery is not evidence. A mystery is a signal that your knowledge is incomplete. Evidence is what reduces that incompleteness. So when you see a viral claim, ask for the evidence ladder. What tests did it pass? What tests did it fail? What data is available? What data is missing? And if someone can't answer those, it doesn't mean they're evil. It means the story is ahead of the science. This is the advantage of a case file approach. We don't need to be first, we need to be correct. Now, I want to add one more concept that keeps people grounded. It's called burden of proof. If you claim not Earth, you must show evidence excluding Earth. If you claim intelligent, you must show evidence excluding natural physics. The stronger the claim, the stronger the burden. So what would evidence of engineering even look like? Let's define it carefully. Engineering is not clean. Engineering is structure that is difficult for nature to imitate. For example, a signal with clear, repeated modulation patterns, information-bearing structure across time and frequency, and behavior that remains consistent across independent observations. And even then, you'd still test, because humans can generate those patterns too. So you'd need sky localization, repeatability, and independent confirmation. This is why serious SETI work is so strict. It doesn't declare a message because something looked pretty. It demands multiple layers of evidence. So if our case ever repeats, that's when the serious questions begin, not now. Now we're in the discipline stage. Now let's set a realistic call to action, scientific, not sensational. What can ordinary people do with cases like this? 1. Learn the difference between unknown and unexplained. Unknown means we need more data. Unexplained often means someone is selling mystery. 2. Reward good uncertainty. When a creator says, "We don't know yet," that's not weakness, that's honesty. 3. Focus on process. Ask what tests were run. Ask what data exists. Ask what would decide the case. And 4. Don't confuse fun speculation with conclusions. Speculation is fine if it's labeled. The problem begins when speculation is presented as fact. That's how legends get locked in place, and once locked, they're hard to undo. So here's our final case file summary in one clean paragraph. We observed a one-off radio anomaly. We applied the standard filters: interference, orbital sources, instrument artifacts. Cosmic explanations remain possible but unconfirmed. The evidence is insufficient for a definitive classification. The case remains open, pending either repetition or a matching identification in external logs. That is honest, that is strong, and that is how real mysteries should be handled. Now, if you want to keep the emotional ending without breaking the rules, say it like this. We listened. The universe answered. Once. And we weren't ready to capture enough. So next time, we'll be ready. Because science is not a single moment. Science is preparation meeting surprise. And the universe is full of surprises. Before we close, one last practical note about follow-up strategy. If you are running a search program, you want two upgrades: more bandwidth and faster alerts. More bandwidth helps you see dispersion, side features, and context. Faster alerts help you trigger other instruments while the event is still happening. You also want long-term monitoring of promising coordinates. Not forever, just enough to catch recurrence if it exists. Because a repeating source might repeat on long timescales. And if you only stare for minutes, you will miss it. So the best modern approach is hybrid. Wide surveys to find candidates and targeted follow-up on the best candidates. That is how the field learns. That is how the map gets filled. And that is how never came back becomes we found the pattern. And that brings us to the real ending. Not what it was, but what it taught us. It taught us that clean signals can be traps. It taught us that repetition is the real prize. It taught us that the most powerful tool is not belief, it's method. So when the next anomaly appears, and it will, you'll know how to think. You'll know what to ask. You'll know how to keep the wonder without losing the truth. This is Space Case Files. We don't worship mysteries, we investigate them. And the file we open tonight stays open. Not because we're chasing a fantasy, because the evidence demands patience. If you want to add a gentle closing hook for the next episode, use this. Next time, we'll open a new file, another real observation, another strange pattern, another moment where the universe did something we didn't expect. And we'll apply the same rule every time. Observation first, interpretation second. Confidence only when the evidence earns it. Because if we do that, the mysteries don't disappear. They become sharper. They become testable. And eventually, some of them become understood. Until then, we keep listening. Final line for the case file. A signal appeared. It vanished. It did not return. And the only honest word for what it is today is unknown. Unknown is not the end. Unknown is the beginning of the next better instrument, the next better method, the next better capture. And if the signal ever comes back, we'll be ready.